the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is yet another video for linear algebra students who are just venturing into matrices and the products of matrices and vectors. And in this video, we're specifically going to talk about how to compute the product of a matrix and a vector two different ways, actually. So to do this, we're going to consider three different combinations here. So AX, where A is defined to be the matrix on the left and X is the column vector on the right. B, which is again the matrix on the left, and Y, the column vector on the right, and C and Z, the same thing. So let's go ahead and compute the products of AX, BY, and CZ as a linear combination of vectors. Now, I don't do this in a classroom because it just takes a little bit of time and it's mostly just computational, but let's go ahead and see how this works here. Now, the very first way that you learn to multiply a matrix against a vector is to interpret it as a linear combination of the column vectors of A. So you would imagine it this way. Each one of the entries in the vector X moves in front of the corresponding column in the matrix A. So for example, the entry in the first spot for X moves in front of the first column of A, and then we'll do the same thing. The second entry in X will move in front of the second column of A, and the third entry of X will move in front of the third column of A. And that will give us a linear combination of the columns of A. Now that doesn't look too bad. We happen to know now how to take the product or the scalar multiple of a vector. So let's go ahead and apply the scalar multiple to each of these vectors. And now we know how to add vectors. We just add entry by entry. Finalizing this with a little bit of arithmetic, we get this kind of interesting vector, -4, -4, -4. And that is the product of A times the vector X written as a linear combination of vectors. So that's how we computed that out. You could do the same thing for B, Y, and C, Z. I'm actually just going to let the video roll as I do B, Y, and then we'll talk about that. All right, here's B and Y, and let's go ahead and find this product here. All right, that time I went ahead and I just quickly did some of the small arithmetic, compressed it all into one move. All right, let's move on to CZ. And finally, adding these up. There we go, that's a product of the matrix C and the vector Z. Now, something you should notice about the product of C and Z. C was this weird looking matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1. We multiplied it by the vector -3, 2, 5. And when we finished all our multiplications and simplifying, we got back down to -3, 2, 5, which is actually what Z was originally. Well, that's because the matrix we multiplied by, what we called C, is a very special matrix. It's called the identity matrix. And we use the notation I for the identity matrix, and some of us will actually write 3, meaning it's a 3 by 3 identity matrix. All identity matrices are square, and you just denote their square size using that subscript notation right there. So if it was a 4 by 4, it'd be I sub 4, and you'd have zeros everywhere except for along what we call the main diagonal here, and those would be 1s. And when you multiply any vector by the identity matrix, and I should say, when you left multiply a vector by the identity matrix, it will return the original vector, just as it did right here. Okay, so the point of this part A was just to showcase how you would do matrix vector products by interpreting the product as a linear combination of vectors, or the columns of A. However, there's a much better way to do this, and that requires us to know something called the dot product. This is something you might learn in maybe Calc 3. However, it's very, very helpful in linear algebra. The dot product, or what we call the scalar product, is First of all, it's a number. It's not a vector. You can multiply two vectors via the dot product. So you could take the dot product of those two vectors and it would return a scalar, not a vector, but a scalar. So again, that's why we call it the scalar product. Anyway, this is an algebraic operation that takes two equal sized or equal length sequences of numbers, so basically vectors, and returns a single number, not a vector, but a single number. Algebraically, the dot product is the sum of the products of the corresponding entries of the two sequences of numbers. Now, I'm not going to showcase the notation of the dot product because that actually does not matter for us in linear algebra, but I will give you an example of a dot product. So find the dot product of these two lists of numbers, which we are writing as column vectors, but they're just lists of numbers, single lists, not a two-dimensional list, not like a matrix, but a single column vector. By the way, they don't have to be column vectors. But anyway, the dot product, what it's going to do is find the sum of the products of the corresponding entries. The sum of the products. So I'll look at the corresponding entries and highlight them. For example, the first entry in V is 2. The first entry in W is 0. The second entry in V is -1. The second entry in W is -8. And finally, the third entry in V is 5. And the third entry in W is 1. We are going to take the products of those like highlighted numbers. That is 2 and 0. -1 and -8, and 5 and 1. And we're going to add up those products. This is the sum of the products of the corresponding entries within those two vectors or those two lists of numbers. When you compute this, you get 0 plus 8 plus 5, which is equal to 13. 13 is the scalar product or the dot product of V and W. So essentially all you're doing is just multiplying the like elements and then adding up all those multiplications. That's what a dot product does. Why is this important? Because guess what? This is a faster way to perform matrix vector multiplications. So part B of our example says perform those same multiplications we did in part A, but this time using the row vector dot product method. Now, what the heck is that? It's probably best seen using this first example, the matrix A times the vector X. Remember what we did? We took this number 1 and we kind of put it in front of this vector, this column vector 1, 3, 6, and then we took the 2 and we put it in front of the second column vector, and we took the -3 and put it in front of the third column vector. But actually what ends up happening mathematically is that in each row of the original matrix right here, we're taking these 3 elements and multiplying them by the 3 corresponding entries in that row, and we're adding them up. That is, we're taking the dot product of this, now I made it blue, of the blue list of numbers and the yellow list of numbers. Now think about that. I took this 1, 2, 3 in blue right here as a list of numbers, and I used the scalar product against this list of numbers. That's what I'm saying I did. Well, let's see if that's actually true. What would be the scalar product of those two lists of numbers? Well, it would be 1 times 1 plus 2 times 2 plus 3 times a -3. Well, that's the same thing as 1 plus 4 minus 9. I hope you recall that list somewhere. Oh yeah, it's the very first row of the result. If you look at the second row of the result, it was 3, 8, and -15 being added up. And let's look at the dot product had we taken the second list of numbers, the second row of numbers in our matrix, and imagine tilting this group in yellow right above it, 1, 2, and a -3, multiplying those and adding them up. You would get 1 times 3, or 3, plus 2 times 4, which is 8, so 3 plus 8, and then -15, which is exactly what we get in this second group of numbers right here. That's a good justification that all you're doing this entire process is performing the scalar product or the dot product over and over again in all these computations. So let's go ahead and do that now in one fell swoop. We'll do it row by row. Remember, row 1 against the vector, or in other words, the dot product between row 1 and our column vector. That's going to be 1 times 1 plus 2 times 2 plus 3 times a negative 3. Now we switch to the dot product of the second row and our vector. We have 3 times 1 plus 2 times 4 plus negative 3 times 5. And finally, we take the dot product of the final row with our vector. Notice, by the way, as I'm doing this, the row that I have highlighted ends up being where I'm filling in the data in our final product. It's pretty helpful. All right, 1 times 6 plus 2 times 7 plus negative 3 times 8. Notice that computation was a lot cleaner and faster than doing the linear combination computation. It's not that the linear combination computation is wrong, it's just a different way of doing it. Here we have 5 minus 9 is negative 4. We have, let's see, 11 minus 15 is a negative 4. And we have 20 minus 24, which is a negative 4. And remember, that was actually what the product of AX was the first time around. Now let's try the product of B and the vector Y. Same tactic, row 1 and the dot product of that versus 5, 2, which is the vector 5, 2, sorry. Remember, we will have a computation for each row here, and we'll write that computation in the corresponding row in this vector right here. So in row 1, we have 1 times 5 plus 1 times 2. Of course, you could have immediately said that was 7, but I'm just showing my work. In row 2, we have negative 3 times 5 plus 8 times 2. Again, I could have easily done the computations in my head, but I'm just showing my work. Finally, row 3, the dot product of row 3 and our vector, 5 times 2 plus 2 times a negative 1. Now we just perform real small arithmetic, 7, 1, 8. Now let's just double check that this is correct. And you can see it does match what we computed before, 7, 1, 8. So it seems to be working out really nicely. The easiest one is going to be the CZ. And I don't mean to make light of it and say like, oh, this is super easy, but you'll see what happens. It's actually really, really nice. The scalar product of the first row and the vector, 1 times a negative 3 plus 0 plus 0. The scalar product of the second row and the vector, negative 3 times 0, 2 times 1, 5 times 0. Well, that's just going to be 2. And finally, the scalar product of row 3 and the vector, and this time it's pretty obvious what's going to happen, 0 plus 0 plus 5. And look how clean those computations are. Much better than doing a product of a matrix and a vector as a linear combination of the columns of the matrix. It's just much easier to use the dot product. Now, before we leave this video lecture, I just want to officially define the identity matrix, the square n by n matrix with zeros in all entries except along the main diagonal, which are all going to be 1, the main diagonal entries are. That is called the identity matrix, and it is denoted I sub n. Again, the dimensions or the size of this matrix, it's an n by n square matrix. And then a small little theorem here, if you have a vector in Rn, so it's a vector with n entries, and if you take the square n by n identity matrix and you multiply it against that vector x, it will actually just return that vector x. This is sort of like multiplication by 1. That identity matrix, however, is going to be very important in this course. Luckily, it's super easy to remember. All right, that does it for this video. I hope that helped out a little bit, especially if you're just learning the computations for a matrix versus a vector. I really recommend working with the dot product version of it, but if you like the linear combination of the columns of the matrix and computing things that way, more power to you. There is going to be a time when that definition will be needed and helpful in understanding structures within linear algebra, but as far as computationally, it is not advantageous. All right, everybody, have a great day. Hope to see you in future videos.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.